Hi, in this video, we'll be going through the solutions to second order differential equations. In particular, we will show why a linear combination will be the only solution. So, the operator we first define an operator. An operator is something that takes in a function as the input and returns a function. This is like differentiating, you still get a function, and your second derivative is also a function. So there's this thing called known as the differential operator, and this is how we write it. So the first order differential operator is as follows. This is a second order differential operator, and this is an integral operator. Yes, it is confusing to look like that, but you must first define it at the start of your question. And one thing to note is the existence of uniqueness theorem for second order ODEs. And this proof is actually similar to the one we had in the first order case, but expanded slightly more. So how do I use this is, for example, we're supposed to find an interval in which it is a solution to the IVP. And so given the differential equation can be written as the following, where Pt is this, Qt is the following, and Gt is 0. Then the only points of discontinuity is when t equals to 0 and t equals to 3. And so the longest open interval which the coefficients remain continuous will be 0 to 3. And this, by the theorem above, will guarantee us a solution exists. As for example 2, we are now supposed to find the unique solution to the IVP of the following form, where PQ are continuous in the open interval containing T0. So in this case, the function y equals to 0 is certainly satisfy the differential equation and the IVP, and because by the uniqueness theorem, it is the only solution of the given problem. So this allows us to find the solution to the IVP with this theorem, or which interval does this IVP exist on. So now we lead to the next theorem, which is known as the principle of superposition. If y1 and y2 are the solutions to this equation, then a linear combination will also be a solution. And to prove this, it is not hard to see that when you substitute the linear combination into here, it actually shows that it will still be a solution. And so for any two solutions, we can then construct an infinitely many family of solutions of the form y equals to c1y1 plus c2y2. But the question now is, can all the solutions be written in this way, or do some solutions differ? And we answer it by introducing this thing called as the Wronskian distribution determinant. So suppose y1 and y2 are solutions to the equation of this linear operator. So the y double prime plus pty prime plus qty equals to 0. And we already know that the principle of superposition states that c1 and y1 plus c2y2 is a solution. Hence, we have to find coefficients that satisfy the initial conditions of the following. And how do we do so is that we must solve the following equations. So first, you just need to sub in. So the first one is when you sub as T0, then this must equals to Y0. The second one is you differentiate it, and then you sub in T0, and this must equal Y prime, Y0 prime. So what do we notice when we have two solutions? We can write it in a linear algebraic manner, so with the use of matrices, as the following. So C1, C2 is your coefficients that we need to find, and we have this coefficient matrix, and it equals to Y0 and Y0 prime. So look at it. Look at this, and with our theory of linear algebra, we already know that C1 and C2 exist if you can like take the inverse of both sides. So that's what we really want. And we just let the Weinstein be the operator of taking the determinant, so of these coefficients over here. So it is actually y1 y2 prime minus y2 y1 prime. And we have a theorem that this solution is the general solution if and only if the determinant is non-zero. So the proof is very simple. You just take any solutions and phi t naught equals to y naught and phi prime t naught equals to y naught prime. From the previous page, we already know if this Wronskian determinant is non-zero, then for all y naught prime, there will be an existing C1 and C2 such that C1 y1 plus C2 y2 solves the IVB. So that literally proves it. If you see from here, if this is the determinant here is non-zero, its inverse exists, and you can just multiply over the inverse on both sides to get C1 C2. If then we say, and note that C1 and C2 solves the IVP, it has to be the unique solution. So this tells us that there will only be one solution to it once you know that the Weinstein determinant is non-zero. And if yt equals to c1 y1 plus c2 y2 is the general solution, then we say that the y1s and the y2s form a fundamental set of solutions. Because we know that any combination will have to look like this because the solution is unique. So it just make a it is just from a combination of this y1 and y2, which are the more important parts. So this part are called the fundamental set of solutions. So we can take an example to understand it better. So let's just take the example 2 of section 3.1, and we see that y1 equals to e to the power minus 2t and y2 is e to the power minus 3t were the solutions of this differential equation, and the Wronskian of these two functions is this determinant. And this actually gives us the minus e to the power minus 5t. Since no initial value is given, it has to work for all values of t, and because the w is non-zero for any value of t, as long as you are able to find one t that works, this will be the general solution. So this, because it works for any value of t, just use t equals to 0, and we are able to construct the solutions for the differential equation in the following sense, where you just take the linear combination. So I hope this is clear on how we understand how the general solution works for a second order homogeneous linear equation. Another example is that we now consider the general solution to this set, and suppose that the function below are the solutions. Then the Wronskian of these two solutions will be y1, y2, y1 prime, y2 prime. When you cross multiply, you get non-zero for all t, because the R1 and R2 are not equal to each other. And thus we say, that's why in the previous video we say that the general solution will be only of the form of the linear combination C1 e to the power R1t plus C2 times e to the power R2t. And now we consider we have another theorem, and this theorem states the following. We consider the differential equation of the form here, and we let y1 be a solution to equation 2, which also satisfies this initial condition, and y2 be another solution that satisfies this following initial condition. Then y1 and y2 must form fundamental sets of solution, and it's not too hard to recognize why, because you just use the Wronskian determinant and see that it equals to 1. Since the Wronskian is non-zero at some point, this y1, y2 must be a fundamental set of solutions, and this completes the proof. And note that the difficulty part of this proof is always demonstrating the existence of the solution. But once we know that they are solutions, then we can say whether they are fundamental set. Lastly, we have another theorem, and is known as Abel's theorem, and is that if y1 and y2 are solutions to the second order differential equation, then the Wronskian function will actually equals to a constant times e, so it's ce to the power minus integral pt dt. So what do you recognize? Well, you recognize this looks like an integrating factor, and there's some constant about it, but we don't really call it integrating factor. Instead, we will just show that the Wronskian, intuitively it will just look like this. So what does it mean? So this means that the Wronskian is either 0 for all t, or it's never 0. Because this part is non-zero, so it's either the c is 0 or the c is not 0. So to prove Abel's theorem, we start by noting that y1 and y2 satisfy the following differential equation, so you just submit in. Then we multiply the first equation by minus y2 and the second one by y1, and we actually add the resulting results to obtain the following function. So this allows us to get rid of this portion over here, the qt part. Then we see that the yt equals to, this is like the w already, so the wt equals to the wy1 y2t, and observe that w prime is actually this portion over here. So this is the w, this is the w prime. So we can rewrite it into the following linear operator form, where it's w prime plus ptw equals to 0. And we can just solve it immediately, because this is the different, as this variable separable, so you should get this following result. Yt equals to ce to the power minus integral of pt dt. And so the value of c depends on which pair of solutions to this equation 22. However, because we know the exponential is never 0, yt is not 0 unless c is 0, in which case c is 0 for all t, and this completes the proof. So we can say that the Wronskians of any two fundamental set of solutions of the same differential equation can only be differ by only a multiplicative constant, and that the Wronskian is determined up to a multiplicative constant. What do I mean? Okay, so we already know that the solutions are of this form. So it can be either you either have ER1T or then C1 plus C2, and this sum maybe you can just have another solution, but it just looks like some linear combination of this, but of course they don't look like E12 or E2T. So in that case you get a different Wronskian, but they only differ by a multiplicative constant. So we just take an example to better understand it. So we got this example 5, and we see that these two are the solutions to the ODE, and we verify that the Wronskian of the two solutions is the given. So we just see, we calculate the Wronskian to be this, and we use the equation above to rewrite this in standard form, and we actually can solve the Wronskian again. It's the following. So you can see how this and this are the same, and they only differ by a multiplicative constant. In particular, in this case, the c just needs to be minus 3 over 2. So I hope you now better appreciate how we understand a second order ODE and why the linear combination will be the only solution, and how we arrive to that is by using the help of a Wronskian determinant. That's all for this video. I hope you have enjoyed it. Please like, share and subscribe, and I'll see you again. Bye!